Today we're going to be begin the presentation with 5 degree of freedom robot based off of a simple mechanism design for industrial pick and place type application. And this robot is a concept robot that allows for inverse kinematics to drive the motion of the actual mechanism. Here we can see the general structure of the robot, where the links are separated into subsystems. Each of these subsystems contain a mass and inertia properties as well as the link structures. In this case, the mass and inertia properties are contained within the CAD components that are attached to this particular link. And we can see here some of the mass and inertia information. These links are connected together with the different joints that gives us each of the different degrees of freedom. We can run this model and take a look at the overall result. Here we can see the simulation of this robot where it's spelling out the word maple, and this is controlled by the end effector location and the inverse kinematics of each of these joints. Additionally, the joints also have a DC permanent magnet motor and controller for each of them to make sure that the motion is as desired. We can take a look at that by going back to the model. We can see here, next to the inverse kinematics block, that we have our motor grouping. Inside the motor grouping is the servo motors. Each of these servo motors has a PID controller that is position based to give us the angle that we desire for each of the different joints. This controller then drives our DC permanent magnet motor. Here we can see the electrical components of the DC machine driving the ideal gear representative of an ideal gearbox. Going back up a layer, we can see that that connects to the output of the motor shaft. We can see that there are multiple of them and that those in turn connect to the different joints of this robot. This robot is an example of a fairly well developed model to show the overall concept of how a robot mechanism could be designed and implemented within MapleSim. It shows several of the different features of the multi-domain connectivity and how the model can be operated. If, however, we're in the early phase of our machine design, then we may want to consider modeling this robot without the final details of what the servo motor characteristics are. For instance, if our motor sizing hasn't been determined yet, or our link sizes haven't been determined yet. So let's take a look at our second example. This model is a pick and place robot mechanism. This model has been specifically designed to answer the questions of what is a proper motor sizing for my robot? What if I vary some of the link parameter characteristics, and how does that affect my robot design? As well as taking a look at some of the bearing calculations to find out what bearing loading I may have. Let's take a look at what the overall simulation is to get a sense of what's going on with this robot. Here we can see the visualization window, and I'll scroll over here a little bit and re-maximize this. So we can see that this pick and place robot is performing a fairly simple operation. The robot itself is following a desired trajectory of the end effector motion, and I can indicate visually what the different motors are going to be doing for each of the different joints. I've done this by these little blocks on the top of the joint connections here. As the motor articulates, you can see that the motor is spinning at a very high speed, and using a high gear ratio we can get the desired motion for the different links. There are 3 motors that result in the revolute motion of this mechanism, providing 3 degrees of freedom, plus a translational component that allows for the pick and place action at the end effector. The results also can plot probed information. For instance, we can take a look at motor speed and torque data. So here I have the 3 motor speed and torque plots right in our simulation window, as well as to find out what the desired motion of each of the joints are. Here we can see the 3 main links, the different angles over time. Going back to the MapleSim model, we can see that the general construct is here, where we have the link structures. We have a sensor component. This sensor component allows us to obtain force information as well as torque information that can be later used to determine radial force, axial force, and bending moment at a bearing. Next to that is the degree of freedom that we have with the revolute joint, and we have that driven using our motor subsystem. This motor subsystem, unlike the previous model, uses a position driver. In this case, I'm using position to actuate the motor. However, if I want, I can always turn this into a motion driver, where I include information such as position, velocity, and acceleration, and have that as the driving input representative of the motor that I'll be using. This is then commanding the overall joint motion, and it has a related gearbox that I can use to help me determine what my operating characteristics for my motor would be. Going back to the top level of the MapleSim model, we can see that that general structure is again repeated with the link, our bearing sensor, our degree of freedom, and motor. And once again repeat it for the base link, and we have our base platform. The model includes inverse kinematics, which have been parametrically specified to allow for a link length for L1 and L2, as well as a different solution type. We can vary our solution type easily by toggling the toggle button and rerunning the simulation. Here, this will allow for the mechanism to be simulated with the second set of solution results that can be obtained with the SCAR-inspired robot pick-and-place mechanism we have here. The model then will show, instead of the elbow link in one direction that we saw before, we will now see the elbow link pointing in the other direction, and we can look at the performance that we see of the model with this new solution set. So now the link elbows are on this side of the solution. These are some of the quick results that we can take a look at when we just simulate our model within MapleSim. However, more powerful analysis may be obtained when we connect Maple to our MapleSim model. I'll toggle the solution set back to the previous one. Attached, I have an analysis worksheet, which when launched will open Maple. This Maple worksheet directly connects to the MapleSim model that we saw. You can see this by the preview window that we have here. You can see the model that's here, as well as the image that was provided with the MapleSim model. By clicking the Simulate button I have here, the background process is that the Maple worksheet will connect to the MapleSim model, run the simulation, and prepare a pre-compiled set of code results. When done, the numerical results from the simulation will be presented. Just like before, we have the ability to look at probed information. We can take a look at what our overall joint length or joint angle information is. Here we can see J1 or joint 1 angle, as well as the minimum, maximum, and RMS values that relate to this joint. We also have plotted multiple other information, such as the angular velocity for the same joint, and we can see the angular acceleration. We can see that there are regions where there are high spikes in the acceleration data, and those could be areas where we can target for our machine design process to try and smooth out the overall characteristics of the motion that we're going to be driving with. When I take a look at other information that's attached to the model, such as the bearing force, I can see that those spikes are also there, and I can anticipate that this will cause additional bearing load on our overall mechanism. Next, I have specific plot generated for the motor characteristics. Here, the motor information can be presented for each of the motors. Each one of these motors have their information presented on the motor side of the gearbox, where we can see the motor speed and the motor torque. The plot points are laid out so that they're data points throughout the performance of the operation. And when we want to be able to compare against benchmark data, we can do something like that by simply toggling our results to take a look at the absolute value. So now we know what our magnitude of our motor speed is and the magnitude of our motor torque is for motor 1. We can directly measure the results by seeing our minimum torque that's used, RMS, and maximum speed. I have also included a feature that allows us to look at motor data characteristics by the attachment of our Excel file here. And what this allows me to do is overlay motor information such as the one seen here. I'm going to select my small motor characteristics to begin with to see if that one is capable of obtaining a motor characteristics for any one of our joints. And by that I mean we can see that our plots are overlaid with the experimental results from our simulation, as well as the data obtained from a manufacturer motor characteristic curve. We can see here in this case, motor 1 exceeds the limits of our small motor information. However, if I take a look at our joint 2, the motor that would drive that has the ability to be within the maximum limits of our small motor. That is the blue line here. But when I turn that off and I look at the characteristics for our small motor of our normal operation, or the nominal value, we can see that on occasion our torque loading does exceed the capability of that motor. Oftentimes this indicates from manufacturer data that the motor may be running a little bit hotter than desired and may require additional cooling. This may not be particularly desirable for your application. So it may be desirable to have the motor perform within the green boundary limits. If we take a look at our third motor, sure enough, that motor is able to perform within the desired limits. If I go back to our first motor and consider a different motor from our manufacturer data list, I may be able to determine a motor that is capable of performing within the desired range. Here, our large motor nearly is able to perform the characteristic that we want within the standard operation of the motor. If I max out what our motor capability is, we can see that the motor limits identify one instance in time where the motor may not be able to reach the desired limit. As a result, I may need to consider different motor configuration, or I can consider different path planning or link configuration, depending on what my design process is for this particular machine. Let us consider the next phase of some of my design iterations. I may need to know information about bearing life. To get that, it'd be very useful to know what the dynamic load is on the bearing joints. This model has the included feature of being able to measure bearing forces as well as bearing bending moments. Each one of the bearings, bearing 1, 2, and 3, have the information plotted here. I can easily toggle the results between them, showing, in this case, the radial load as well as the bending moments. In each case, you can see a very harmonic set of results, and that's because if I take a look again at our simulation, we run the simulation through once and then repeat the process multiple times. As a result, we would expect to see the same kind of behavior on each one of the loops and see the spikes rather repetitively. Going back to the Maple analysis sheet, sure enough, we can see that there are two distinct patterns in our bearing loading. One, a very large spike, and then the second one at the lower spike. These 2 points relate to the two ends of the desired path that the desired path that the robot actually performs in. During the pick and place operation, where the end effector goes up and down, is a particular time where our bending moments may incur large magnitudes and spikes as the end effector is actuated. These could be areas where our bearings may become overly loaded, and changes in the design either through making sure our bearings are stronger or perhaps changing the way that the end effector is actuated may need to be considered in the design process. Lastly, if we want to be able to apply this information in a more generic sense, it can be extremely useful to take the results and export them to a data file. Of course, we have that ability where I can just simply dump the entire set of simulation results to a file. I can simply take that as Excel data, where I have information that relates to all of the data that comes out of the simulation. In this case, we're able to plot out the time on the first column, and we can see the radial force, bending force, and axial force for each of the different joints going across, as well as any of the joint angles, accelerations that we may be interested in. This then can be used as part of any of the bearing analysis software that we may have, or as part of our load and life calculations. The last feature that is listed in the parameter sweep is the parameter sweep tool in this model. Here we can change the link lengths. For instance, link 1, I have a range from 0.4 meters to 0.45 meters, and link 2 I have set to the same value. So I'm only sweeping through changing values of link 1. I can run the parameter sweep analysis. It's a very fast process by using the multi-processing and multi-threading capabilities of the computer that I compiled on here. And that's an automatic feature that comes as part of the parameter sweep tool. The results shown here allow me to take a look at the motor performance characteristics for each of the motors. And you can see that there are significant variations in motor 1 loading characteristics just by slightly changing the length of link 1. Here I have swept through 3 different parameter sets, and I can configure this into a similar look like we had before, where I can take a look at point plot data and consider the absolute value for each of these. And I can make sure that the envelope in which these are performing in is within the range that makes sense for my motor selection. Additionally, I can take a look at how different information appears through the parameter sweep, such as joint 1 velocity information. We can see that there are significant variations in the joint angle as the swept parameters are changed, and that the loading will then change throughout the entire mechanism just by changing the dimensions. If I go back to my parameter sweep settings and I want to include any additional information, I can. For instance, I can change the range that I'm going to perform my parameter sweep in, and we can see significantly different results. As we can see here in our angular velocity, we have very different output behavior, as well as in our motor information, we can see that the results have significantly changed. If I go back, I can easily toggle those results and compare and see that the overall tendencies converge closer to the origin of my motor torque plot. Here I'm only comparing against 3 different configurations by toggling the parameters of link 1. I can easily include the dimensions for link length 2, By performing this parameter sweep, what I'm toggling is 3 different points for length 1, 3 different points for length 2. And when you multiply those out, that's 9 possible configurations. And we can see how quickly that was solved using the parallel processing. And you can see in the legend all the different lengths that are used in the model. Now we can see very significant variation in our overall performance. For instance, in the joint angles, we can see that there are, in fact, non-trivial changes in the model, where the results are no longer just overlaid and converging onto each other. In fact, they have different crossing characteristics. Our motor speed and characteristic behaviors are becoming significantly more dynamic, and we can tell that the overall system behaviors is significantly changing by changing significantly the lengths of our different links. We can take a look at any of the motor characteristics that we were interested in and see the same result occur. This overall tool has been developed using Maple as the analysis program that is connected into our MapleSim model. The model itself has been configured in a way that allows for the mechanism to reveal this information by separating the motor information from the link structure and using the inverse kinematics to drive how the motors are actually going to be actuated. The bearings and the representation of them have been separated such that the motors can be attached to their fixed structure, and on the other side, the actuated side of the bearing can then adjust the different lengths. By configuring our model in this case, we can reveal insight into the overall design characteristics that we may have for this pick-and-place robot. We have the ability to always go back, change any of the parameters we may have, such as our gear ratios. I can change my gear ratio 1, gear ratio 2, and gear ratio 3 to a completely different configuration and simply run those results again. The model is allowing me to have a very parametric approach to this analysis without being confined to limitations that may occur by selecting a motor and configuring it with a DC motor that we saw in the first example. This allows me to examine different possibilities, such as what-if scenarios, and consider that my design may change and I may need to go and have multiple iterations in my overall workflow without being tied down into any decision making that I may have further in the process. We can always run the analysis worksheet with these new configuration parameters simply by clicking on the simulate process once again. Now that we have our different gear ratios, the MapleSim model will be re-simulated using our new set of results. Of course, we can probe the results like we saw before, and now we can see our new set of motor characteristics for each of the different gearing configurations. And then now we can consider that the small motor is possible with some of the other configurations, if at all, and we can always look back to see how far off we are now with the maximum motor. This is always possible to simulate the results with any of the parameter sweep tools. Can be done on other parameters throughout the model, and take a look at those simulation results once again. In this case, the lengths are the ones that I've used in this model. However, you're not limited to that in the slightest. The design process will then allow a user to create the model that makes sense for them. And once you've decided on some of the motor sizing and overall model configuration that you want, the next step will be to move towards like the first model example we have here, where the lengths have been determined and included with CAD information, allowing for very accurate mass and inertia information, and servo motor information that now can be driven with the inverse kinematics, connecting those servo motors together with PID controllers to allow for a position controlled system, and together develop the model that you want to be able to perform the overall task that you're looking for. This process allows for an iterative approach to your machine design, where the model is no longer limited to pre-selecting any of your configurations, either through link lengths, inertia properties, or motor selections, but still has the ability to expand upon that information and include higher dynamics that can occur from your controllers or your actuating devices.